Finally, we're going to learn about our last type of two-sample test called the paired two-sample test. This test is used for a very different reason than our previous two tests. Specifically, it's used when the data collected is not independent. A dependent sample means that one sample is directly linked or matched in some way with another sample. So one group would depend on the other. If you have this dependent relationship, then you must use the paired test. So our previous test, Welch's and pooled test, were used for independent samples. This test will be used for dependent samples. There are two ways that your data can be paired. The first is with matching observations. So for example, if you wanted to compare the same customer spending in December and January, that would be dependent because it's the same person being used twice. Or maybe two real estate firms appraise the same property. Because they're looking at the same house, then it will be paired or matched on the house that was being assessed, even if it's by two different companies. The other type of way you can get a paired test is when you have a before and after test. So think about it like if a student completed a test, then they got tutoring and had to write the test again, and you wanted to compare their scores before and after, then this would be dependent data because it would depend on each student. Another example is maybe they look at your spending on a credit card, then they give you an incentive, like if you spend this much this month, we'll give you a free trip or free $100 extra savings or something like that, and then they look at your spending again after the incentive. That would again be a before and after test where you're looking at the same person's spending, so that would also lead to paired or dependent data. There isn't a statistical test to determine if data is paired or not. You really need to decide just by thinking about how the data was collected. So before we actually get into the math for how to conduct a paired test, let's talk about some examples of how you determine if your data is dependent or independent. If it's dependent, we'll say paired because we're going to need to use the paired test. So for the first example, we have a fitness study that records each participant's resting heart rate before starting an exercise program and again after completing the exercise program. This one is a before and after test. They're looking at the same person before and after, so this data would be dependent or paired on each person. The second example says you want to compare the average number of hours of sleep for 25 randomly selected college students and 25 randomly selected working adults. Should how much a random college student sleeps impact how much a random adult sleeps? If they're not related, no, this would be independent. For number 3, we have an education researcher measuring math test scores for the same students at the beginning of the semester and again at the end of the semester. Again, this would be a before and after test, which means it is paired data for the same students. For number 4, a researcher compares the average GPA of biology majors and chemistry majors at a university. If the biology majors and chemistry majors are not related to each other in any way, then this should also be independent because a random biology major shouldn't influence the GPA of a random chemistry major if they're not working together or related. Finally, reaction times are measured for a participant using their right and their left hand. That's matching observations. That right and left hand are two different things, but they're for the exact same person. So because they're matched on the person who the hands belong to, this would be a paired test. So for number 1, 3, and 5, if you wanted to look at the differences between the two groups, like left and right hand, math test scores at the beginning and the end of the semester, and heart rate before and after the program, to compare all of those two groups, you need to use the paired test. So that's what we're going to look at next. What are the steps for conducting a paired t-test? The first is to write out the hypotheses, and the hypotheses actually look a little bit different than for the other two sample t-tests. The reason for this is because the paired t-test means that the results are matched in some way. Instead of focusing on the difference in the means between the two groups, we'll actually focus overall on the differences, just as one variable. What I mean by that is if you look at an example of data, in this we're talking about construction. So they're basically making a structure, and they have piles, which would be like support pillars made of concrete essentially, and they estimate how much material they'll need for it, and then they measure the actual amount they need for it. If we find the difference between the actual and estimated amount for every single individual observation and then fill this in, all these differences are what we'll base the paired t-test on. By focusing on those differences, we can write the null and alternative hypothesis in terms of the mean of the differences. Technically, with a paired test, what we'll be testing is the mean of the differences 0 in the null? And in the alternative, you can either test if it's not equal to 0, greater than 0, or less than 0. The wording in the question will be the same as for any other two-sample test, just how we write the hypotheses is slightly different. You need to write them in terms of one mean instead of in terms of two means. For conducting the test, first you need to make sure your data is sorted into groups according to the two groups you have. Once it's sorted into groups, you'll need to choose from the data analysis toolpack the option for the t-test that says paired. Just like all the other tests, we'll choose group 1 as the group with the larger mean and group 2 as the group with the smaller mean. For the hypothesized mean difference, we'll use 0. And for the level of significance, we usually use 5%, but that's typically given in the question on assignments or homework. Finally, once you get the output from the test, it's going to look very, very similar to this output. For our other tests for independent data, it's going to look similar to this. You'll find the correct p-value and then make your decision to reject only if the p-value is less than alpha. So let's look at our example for conducting a paired test for this data that I mentioned earlier on pile length. So it's a construction data set, and we're looking at the differences between how much material they estimated they would need and how much they actually need. For the null and alternative hypotheses for a paired test, you can always write them with this mean of the differences symbol. So I'll type that in. Mean of the differences will be what's in your null and your alternative. So anytime you're doing a paired test, mean of the differences is what you put as your symbol. Then for the direction of the test, this one says we want to just see if there's a difference in the actual and estimated pile lengths. Just looking for a difference means we want to do the not equal to test. So I don't have to find that symbol again. I'm just going to copy and paste it from my previous sheet. There we go. And we're going to just test against the value of 0. Like I mentioned here, the hypothesized mean difference, we'll use a value of 0 to say, are the differences 0 or not? So with the paired test, what we technically want to see is if the average of this whole difference column is equal to 0. Average of the differences right now, we actually calculate it, is 6.38. So what the statistical test should tell us is 6.38 for the average of the differences close enough to 0, or is that actually considered a significant difference between the two groups for estimated and actual length? To get a p-value for this, to see if it's significant or not, the easiest way is once you've written out your null and alternative, to go into your data analysis toolpack and find your paired test. Just to reiterate, this would be a paired example because we have kind of a before and after in estimated and actual length for the same piles. So anytime you're doing before and after, this is paired or dependent data. For variable 1 range, you should choose the range with the larger mean. Here I didn't calculate the means individually of the actual and estimated lengths, but when I calculated the difference, I took the actual values and subtracted the estimated values. Most of the differences are positive, and the average was positive. So because I got a positive number when I did actual minus estimated, that means that the actuals are longer on average. So I'm going to select the actual column first, and then I'll select the estimated column. This data is structured in a different way than the previous examples, where we had to be careful about sorting according to yes and no. This data is already stored in two separate columns, but they're still different groups for estimated versus actual. It's just how the data was chosen to be stored, that they put the two groups into two different columns and they're matched on the same pile number. For my hypothesized mean difference, I'll still have a value of 0. And this time I did select the labels just because of the way that it's sorted into two different columns. I have the headers for the columns, estimated and actual, already written out for me. If I check that box because I selected the labels, my final step is just for the output range, where I'm going to place it below my hypotheses. Once I press OK, like I said, it will give me a very, very similar output to what we had for the previous example. Notice that it's correct that the mean of the actual lengths is longer than the mean of the estimated length, so it is the one with the greater average. We selected the right one first. Also notice that the number of observations has to be the same. That's because they are matched on the same pile, so we need to have an estimated and an actual length for each pile. So you need to have the same number in each group. Whereas for the pooled and the paired test, we had different numbers in the different groups. That didn't matter. For the paired test, you should always have the same number of observations in each group. That can be another hint that you have to do a paired test, but you could also have an equal number in each group for independent tests, so that's not the only way you can decide. You have to think about how the data was collected. Like in this case, we have the before and after test, estimated and actual. Finally, just like for our other type of tests, we need to look at the p-values. We have two of them, one tail and two tail. You would choose one tail if the alternative is greater than or less than. Here, our alternative was not equal to, so that means we look at the two-tail option. This p-value is written in scientific notation. It's really 1.1188 times 10 to the negative 23. This is an extremely, extremely small number. Essentially, it'd be like 0. Then there'd be 22 zeros. 1, 2, 3, 4. I don't even know if I'm counting 22, but there'd be like 22 zeros in front, then 112. So however many you make 22 here, that's how many you'd have to write out to write that number. So this is essentially 0. At the 0.05 significance level, a p-value of essentially 0 is definitely smaller than 5% alpha. So this time we got a p-value less than 5%. The decision should be to reject the null hypothesis. The null hypothesis was that the mean of the differences is 0. We're rejecting that. So what that means is that the mean of the differences is not 0, which I calculated the mean of the differences. It was 6.38. So what this is telling us is 6.38 is too far away from 0. They're not the same. How we actually write that out is there is a significant difference between the estimated and actual pile length means. So because we got a reject, that means they're not the same for the two groups. We have a difference. On average, the difference is not 0. 6.38 is considered statistically significantly different from 0. And that is the paired test. The actual implementation for the paired test is very, very similar to the pooled test and Welch's test. All you have to keep in mind is number one, you need to think about how the data was collected. There's no test to determine if data is paired. You need to decide based on the wording in the question. If you've decided on a paired test, you'll write the hypothesis slightly differently. You'll write it in terms of the mean of the differences instead of writing it as two different mu's subtracted. You just want a single mu of the differences. Then the output looks pretty much the same. You find the p-value you need, compare it to alpha, and make your decision. Thanks for watching. In the final video, we'll talk about confidence intervals for all of our two sample tests that we've learned so far.